and he's also PD Pro Professor of Physics at the University of Helsinki. He is a fellow of AAAS, AGU, and AAA, and his contributions have been recognized with major honors, including the Benjamin Blue Prize, the Joram Kaufman Award, the Fuchs Memorial Award, and the ACS Award for Creativity in Environmental Science. With more than 600 publications spanning chemical kinetics, aerosol chemistry, and influential laboratory and field studies, Dr. Worsnop has played a defining role in advancing the understanding of atmospheric gas-particle interactions. On behalf of IITM and everyone gathered here, I welcome Dr. Worsnop to give the 87th Ananthakrishnan talk on atmospheric aerosol chemistry, climate, and environment.
Thank you. This is my second time here today, and I hope it's not my last time. And I intend it not to be my last time. So, the purpose of this slide serves several purposes. First, as you just heard, I have been in Aerodyne research now for 40 years. And then the second purpose is about 20 years ago, I became a professor, visiting professor, part-time professor in the University of Helsinki. And then, somewhat coincidentally, about 20 years ago, I started spending a lot of time in China. And the purpose of this is all those institutes I'm actively collaborating with. And if you notice, there is IITM Pune is at the end of the list. Because in order to get on this list, we need to have a paper together. And Pune is my only collaboration so far in India. And I've been telling everybody this week and last week, I'm looking for more. Okay? And the other purpose of this is that everything I'm going to show in this talk is a collaboration with a whole bunch of different folks. I don't do any real work myself. But I work with students and postdocs and professors everywhere. I mean, as you can see here. So this is all collaborative work. And finally, as you heard, I mostly do, almost all the work I do, the vast majority, is applying mass spectrometry to online continuous measurement of the air, the aerosols in the atmosphere. 1 micron is an aerosol particle. 1 nanometer are molecules or molecular clusters in the air. And so that's what I do. And this is my favorite introductory slide. This is a picture from Pittsburgh in the eastern United States, taken in 2001 during the Pittsburgh Air Quality Study, PAQS, which was it was actually the second EPA supersite study to study the chemistry or the study PM 2.5 in Pittsburgh. And this is a picture from 2 days in 2001, a clean day and a dirty day, a polluted day. And whenever you see a picture like this, the first thing you should know is the distance of the camera from that skyline, which is 10 kilometers in this case. And what's significant about this is this polluted day, the PM 2.5 was about 45 microgram per cubic meter. And on that day in 2001, the EPA daily standard for PM 2.5 was 65 microgram per cubic meter, which means, according to the EPA then, this was a clean day. Several years after this, the daily standard was reduced to 35 microgram per cubic meter, where it is now. And the annual standard has been reduced successively until it was 12 microgram per cubic meter. But that's no longer true. Since 2 weeks ago, our current government announced there is no PM 2.5 standard anymore. But anyway, now what's important about this is that a day like that in Pittsburgh, if you took a satellite picture, then you'd see that this haze in Pittsburgh is actually all over the Eastern United States. And it's a regional event. And often that haze would be advected over the Atlantic Ocean. And what's important here is that called the aerosol direct effect. When you have haze like that over the ocean, let alone some clouds to go with it, over that dark ocean, that is the most dramatic global cooling there is, almost. Except only a cloud is, that's tens of watts per square meter. And the other point about this picture is that days like this don't happen in Pittsburgh anymore. They just don't happen. Now, to put this in perspective, I'm going to show this slide. This is a very simple canonical picture of the energy balance of the Earth's atmosphere. We have 340 watts per square meter coming in from the sun. The important number for me as an aerosol person is that roughly a quarter of that sunlight is reflected directly back into space off of aerosols and clouds. Now, we are increasing, as we all know, we are increasing CO2. That's the greenhouse gases right here. And the effect of the CO2, 100 or 200, 100 going on 200 part per billion extra CO2, is 2 or 3 watts per square meter. Now, that's all it is. That is roughly 1% of the incoming radiation. And the average temperature of the Earth is 278 K, or what? 1% of that is 3 degrees C. That means the 200 part per million of CO2 is going to warm the Earth by 1%. I mean, the calculation is that simple. Okay? The forcing is 1% of the total. The Earth, if we trap an extra 1%, we get a 3-degree warming. Now, what's important to me is that same 2 or 3 watts per square meter would represent a 3% change in that number. Now, all these calculations are from the IPCC model, global models, and they're comparing today with 1750. And the simple fact is, we have no idea at this level of accuracy what this was in 1750. We know there were clouds. We know there were aerosols, but we don't have any idea at the 3% level. And so, I mean, we don't know, and we know that since World War II, since the industrialization, the CO2 that's when the dramatic increase in CO2 was, and there's a dramatic increase in aerosols and haze. The United States has cleaned it up. Okay? Europe has cleaned it up. when we cleaned it up, China, conveniently, China started making air much dirtier. So that you make the same satellite pictures of aerosol coming out of China into the Pacific Ocean. So they compensate from a global warming cooling standpoint. The Chinese compensated, but they've cleaned it up. Now who has the headlines? India has the headlines. Now you're compensating, okay? See, I'm not making this up. We are cleaning up our air because we don't want to breathe this stuff. We don't want to look at it. We don't want to breathe it. Okay, in the US, the EPA first regulated, starting in 1970, total suspended particulate. That was smoke coming from steel mills and dust coming from cement factories. Those were the two biggest sources of total suspended particulate in the United States. Then they moved on to PM10. And then finally in 1997, they established the first PM 2.5 standard. And that's when the Pittsburgh air quality study happened. Right now, China has moved to a PM 2.5 standard. India is still on a PM10 standard. But I'm just making the comment that if we all do that, we're gonna make global warming worse. Okay, and climate change worse. And we should all know this, okay? And I'm not gonna say anything else or almost nothing else about climate in this talk, but it's just true. Now, so the 1997 is when the EPA in the United States established a PM 2.5 standard. And by coincidence, in 1995, John, Jane, and I built the first aerosol mass spectrometer. I'm not going to try to explain this particularly. Just to note, there's an aerodynamic lens that samples ambient air and magically focuses the submicron particles into a beam that we shoot down a vacuum chamber. I should note that aerodynamic lens was designed by Peter McMurray's group at the University of Minnesota. The key here are all these vacuum pumps that pump away all the air. We impact the aerosol on the oven at 600 degrees C and ionize them with electron impact and then measure the positive ions with a time of flight mass spectrometer. From my point of view, this is a simple molecular beam mass spectrometer. It's very similar to the instrument I worked on as a graduate student, much simpler version. And that instrument happened to be developed by this guy named Y.T. Lee, who is now the most famous scientist in Taiwan. He was a postdoc in the group 4 years before I joined my graduate group. He was a postdoc, he built this instrument, he went on to build 6 more of them, Chicago, Berkeley, and Taiwan. And then he happened to win a Nobel Prize for this instrument, or the experiment we did. From our point of view, this is just a particle concentrator. We inject from 2 liters a minute, 1 liter a minute, all the flow, and get all of it to the detector. But only 1 in 10 to the 7th of the air molecule that the aerosols were suspended in get to the detector. That's a particle concentrator. The other critical thing is this detector. We have the aerosol beam in high vacuum. It's this tungsten oven at 600 degrees C. Everything vaporizes. Everything that vaporizes intersects this electron beam. We detect everything in that vapor plume, make a bunch of positive ions that then we analyze with a mass spectrometer. We call it the non-refractory component, i.e. everything that will vaporize is 600 C. That's almost everything with the specific exception of dust and elemental black carbon. And now we have a laser and we can detect black carbon. But we get everything that was in that aerosol that gets vaporized. We ionize quantitatively with high sensitivity. We get everything together. We get a mass spectrum that looks like this. We've subtracted out the air, nitrogen, and oxygen signal, and everything that's left came from the aerosol being vaporized on that oven. And you have all those colors in red, all the colors, which means we can easily separate the inorganic from the organic. Sulfuric acid gives these peaks, nitrate gives these peaks, ammonia, these peaks, and then we have some organic peaks. I just labeled the two most important ones, the 44 and 57. And we spend most of our time trying to interpret those green peaks. And you can see we can turn these signals directly into aerosol bath loading. Now, what I like to say about this mass spectrum, especially to all the young people in the audience, that I think there are roughly 1,000 people who know this mass spectrum and the colors by heart. And anybody who learns this mass spectrum, how to acquire it, how to analyze it, how to interpret it, or the other mass spectrum, is employable. Okay? If you know how to do this, you can get a job somewhere. Because there are now 300 of these instruments, another 200 chemical ionization mass spectrometers, and they all need operators, students, scientists who know how to interpret the mass spectrum. And it's not trivial, but it's important. I'm just saying that, okay? So this is the original, okay, yeah. Okay, now inspired by last week, Spiros Pandit from Carnegie Mellon, now the University of Padras in Greece, who was the leader of that Pittsburgh air quality study at Carnegie Mellon. He gave a talk. In his talk, his keynote address, the first talk in the meeting, he made a big deal that we use my word, that the AMF changed everything. And this is how the AMF changed everything. This is an old slide now. I haven't shown this slide in probably 15 years. But one of the original slides from Pittsburgh, that Pittsburgh air quality study, when we were first understanding what the AMF data meant. The colors are all wrong, but the data is still true. We're looking at the black traces. The top panel is this M over C57, which is mostly C49H plus. See the black, and then in the red is CO. I mean, I remember when we first saw this. This is amazing. What we now call HOA, hydrocarbon aerosol, track the CO amazingly well. And that's because they both come from the same source. In this case, it's mostly diesel trucks. And it has, and then down below, we have this M over Z44, CO2 plus. Again, black straight. And it has a diurnal pattern that more or less tracks ozone and the sunlight. But it tracks ozone better than the sunlight. You can just look here. And then suddenly here, it starts going up. I mean, the M over Z57 tends to go to 0 at night. Because it's local primary aerosol. When this starts going up, that's called a Haines event. I mean, to cut to the chase, that's secondary organic aerosol increasing. And this is just two different ions in this crude mass spectrometer, okay? And to quote Spiros Pandit, and I remember this really well because he and I argued about this for a couple of years. There's much more secondary aerosol than primary aerosol. And that's true in Pittsburgh, and it's true here. And that's the whole message of my talk. Okay? Now we have a high resolution time of flight mass spectrometer, and we can measure all the individual, identify molecular formulas and all these different ions we have the color scheme here. The green is hydrocarbon. It doesn't have much oxygen. The OOAs are dominated by purple. And then you have biomass burning. That's a combination of green and purple. And the purple particularly is at M over the 60 and 73, which is a marker for levoglucosan and other sugars that come from the thermal decomposition of cellulose. You know, oxidized. So this is hydrocarbon. It turns out that in ambient air, at least in the past, that's mostly lubricating oil and diesel soot particles from trucks. This is semi-volatile organic, and this is low volatility organic. This is more oxidized than that. This is relatively fresh. This is aged. And now we get factors like this and AMSs all around the world that led directly to this paper. Did I move this? No, I can't. This science paper in 2009 that now has well over 3,000 citations, where without trying to explain it, except to say, this is 40 campaigns from 17 institutes. I used to say around the world, but then I realized it's really only the Northern Hemisphere, because we didn't have any measurements in the Southern Hemisphere then. And to summarize all this, what it says is that roughly half the PM 2.5 submicron aerosol, this is really PM1, but PM1 and PM2.5 are mostly the same. But the submicron aerosol is roughly half inorganic and organic. That wasn't new, but this was still the most comprehensive semi-global measurement. But much more importantly, the average O to C ratio was 0.7. That means the average carbon-containing molecules in ambient suspended aerosol, submicron aerosol, have 0.7 or more oxygens per carbon. And at the time, people didn't believe that. It's twice as high as people thought from smog chamber studies. And it's still true that AMS is the only instrument that can directly measure that. And the rest of my talk is about where that oxygen comes from. And the other detail I like to note about this is in this paper, the cleanest pie chart was in Huhtala, a station, fourth station in central Finland. And the dirtiest, most polluted was Beijing and China. Now, since we published this, the two places I have studied the aerosol most are Huhtala and Beijing. Now, what's important, this is actually PM1. This was measured in 2006. And during a haze event, when it's really polluted, PM 2.5 is normally about twice PM1. When it's relatively clean, PM1 is 80% of 2.5, PM 2.5. But so PM 2.5 was about 150 then, and it got much worse. By 2013 to 15, 150 or 200 might be a better number. And then since 2015, it's come down below 80. And that's the history. And to my point, we measured it, okay? I'm on many papers about that history. And the final note about this figure is, you notice this legend which talked about the details of the O to C. It's sitting top of India. And the reason it's sitting on top of India is we didn't have any measurements in India in 2009. It's that simple. We do have measurements now. And now you win, okay? Delhi or Northern, IGP wins in the winter. And I'm gonna come back to that, okay. My other favorite slide, rest of my talk, or this talk, is a collection of my favorite slides. And so, in 2005, we took our Aerodyne mobile lab and drove it down to Mexico City and drove it on top of this small mountain. I should find out. This actually matters. I can't even remember the name of the mountain. Or more importantly, how high it is. It's maybe, I'm gonna guess 800 meters or something, overlooking Mexico City. Mexico City is a mega city of 20 million or 25 million people, and it's unique because in Mexico City in the morning, when the air is coming from a plateau way out there, the air is really clean. And then we would watch every day the haze start forming down below and rise up to it here on that mountain. And what you see is both the second OOA, oxidized organic aerosol, which is SOA, secondary organic aerosol, and ozone were relatively low in the morning. And then we watch this happen every day. This is the first direct proof that this OOA is coming from the same photochemistry that makes ozone. You can't see this, I've never seen this anywhere else in the world, because when in polluted cities, it's never clean in the morning like this. And there's another minor detail here. There's a biomass, we have something labeled as biomass burning. We know that it was a fire over here, some sort of trash fire or waste fire, we don't know. And what's interesting here, we clearly saw aerosol from that, and that particular fire plume didn't make any ozone. It is still true that we don't understand ozone production from biomass burning. Some fires make ozone, some don't. That's another research topic, but here it is. So I put this all together. Everything I have told you is about secondary versus primary. This is, it doesn't matter, but this is the sort of reading that blog. But primary aerosol is aerosol that's directly emitted as aerosol, which mostly is combustion. I mean, dust and sea salt are the other examples, but I'm not talking about that. But and then secondary is if gases, they get oxidized and then form sticky, low volatility gases that mostly condense on the pre-existing aerosol, can also nucleate, even get reactive in clouds. But the key point so far is the secondary is much larger than the primary. And in starting in 2004, this was news. In 2004, we started believing what the MORC 44 CO2 plus signal was telling us. And it's the same chemistry that makes ozone. Now, it was exactly at this point that I was recruited to Helsinki in Finland. Now this is a schematic of the natural aerosol life cycle, ignoring burning or other direct emission. Combustion, I should say, not burning, combustion. So in the relatively clean atmosphere, and so we're looking at the aerosol life cycle from 1 nanometer to 10 nanometers to 100 nanometers, which are CCN particles, cloud condensation nuclei, which I believe you guys know something about. But what I just told you is that the CCN particles, the particles larger than 100 nanometers, are dominated by organic, or oxidized organic, and sulfate. If you're near a city, near an urban area, you can see, significant amounts of ammonium nitrate. Now, this is the point that I was hired in Helsinki. And I was hired in Helsinki to figure out what the chemical composition is of these molecular clusters that initiate nucleation and nanoparticle formation. And the key for the molecular clusters is there are a few really sticky molecules, low volatility molecules, where sulfuric acid is the favorite molecule historically for nucleation. There are also some sticky organic molecules, green ones. But the point about this picture is that 99% of these molecules actually condense on this. Okay? The number of molecules that act, even most of the clusters here, if they form clusters, end up coagulating with the background, what we call the condensation state. So when you try to figure out which few of these molecules actually make a cluster that survives and grows a nanoparticle, you're really studying a large fraction of this chemistry, because these molecules all end up there. So that's when I went to Helsinki. And in 2009, we invented something called the Appitop. All this stuff on here is just the stuff we use to try to calibrate it. It's really an atmospheric pressure. We're just sampling atmospheric pressure ions to take the time of flight mass spectrometer and open it up directly to the atmosphere and just measure the ions in the air. In this room, there are probably 1,000 to 2,000 ions per cubic centimeter. Most of them are formed by cosmic rays. A few from radon. If you have radon coming out of the soil here, that creates some more ions. But the idea is we're just going to look at the ion in the air. It's an atmospheric pressure interface time of flight mass spectrometer. It was put together by these people. All of them are professors now. These were all PhD students in the beginning. The first PhD students I worked with in Helsinki. Then 3 of them are full professors and the other is an associate professor. So the very first day and night in April 2009, when we took this Appitop to Hutila, this boreal forest station, this is what we saw. In the day, we saw sulfuric acid clusters. Monomer, dimer, trimer, tetramer, and the tetramer even had some ammonia in it. This was amazing. The appearance and growth of these clusters is exactly coincident when the nanoparticle counter saw a nucleation event at 10 or 11 in the morning. This was so beautiful, and it's what we expected, more or less. We thought sulfuric acid and ammonia played a big role in nucleation in Hutila, but then we kept it on, and at night, we saw a completely different spectrum. At night, the sulfuric acid goes away. When the sunlight goes up, when the sun goes down, all the sulfuric acid in the air just condenses into the aerosol. Without sunlight, there's no sulfuric acid production. If you're an atmospheric ion person, there's always enough nitric acid around, so that the nitrate anion becomes the largest anion, or largest concentration anion in the air, and we see this spectrum. Okay, at a peak 300 to 400, and then 500 to 600. Now, it took us a year to figure out that this ion at 340 is C10H14O12 N minus. It took us another year to realize this is really C10H14O9 clustered with an NO3 minus. And this is remarkable C10H14O9. This molecule is in the gas phase. The primary precursor, they're almost the only VOC in spring inhutula, is alpha-pinene and a couple other terpenes. Terpenes have a molecular formula of C10H16. It looks like we were able to add 9 oxygens to alpha-pinene while only losing 2 hydrogens. Now, 2 things happened. We suddenly realized we were using the atmospheric nitrate anion to detect these highly oxidized molecules. So we invented immediately, well, the nitrate sim, invented isn't really the right word. We added a nitrate chemical ionization source to our time of flight mass spectrometer. This is the same epitop, but now still sampling atmospheric pressure air, but we are sampling 10 liters a minute of ambient air, and then we're adding in the sheath flow, which is about 20 liters a minute, nitrate anions. Now and that's what's called an Isley type chemical ionization inlet. Now, Fred Isley was one of my heroes. He is actually the first person to detect ambient ions in the atmosphere, and the first person using this nitrate source to detect sulfuric acid mainly. But he used a quadrupole mass spectrometer. And I don't remember when, but I told him I wanted to use a time of flight mass spectrometer, replace the quadrupole with time of flight, and he told me it would never work. But it did, and we get effectively 1,000 times more intensity, and we can see this. I mean, this is my story now. So I went the wrong way, sorry. I mean, where am I? Fred Isley knew there were signals out here in his quadrupole, but he wasn't in Utah with this nice, beautiful spectrum. But there were a bunch of tiny signals here, but he had no way of ever figuring out what they were. And if you have quadrupole, if you look at all the ions, you reduce your sensitivity a lot. So that's my version of where the epitop and all the things came from. So when Kyle N, after he got his PhD, moved to a postdoc in Jülich with Thomas Mendel and Jürgen Wilt and Joe Thornton from the University of Washington, was on sabbatical during that year. And all they did is they mixed ozone plus alpha-pinene and what was then called the Jülich plant chamber. And they saw the same spectrum we saw in Utah. Okay? And so you're making highly oxidized organic molecules, some extreme low volatility organic, C10 and C20 molecules in the gas phase with really high O2Cs. To make and we know now that they participate in nucleation and nanoparticle growth. But in the context of my talk today, most of these molecules, as I said before, condense on the background aerosol. Outside of really polluted regions, this is one of the major sources of that extra oxygen that the AMS detected. And what is true also, in the spot chamber experiment before 2000 or even 2010, they used high concentration and they made a bunch of other stuff, and all this stuff went to the wall and they never thought. So the question is, where did this come from? And it's something called auto-oxidation. Without going too much detail, if you OH or ozone extracts the hydrogen, you make an alkyl radical in the atmosphere, 20% oxygen in the atmosphere. That alkyl radical becomes adds oxygen that becomes a peroxy radical. That happens in microseconds in the atmosphere. And then that peroxy radical can extract a nearby hydrogen and form another alkyl radical that forms another peroxy radical. And I'm not going to go through the details, but you can add 3 or 4 or 5 oxygen molecules in seconds. And it turns out the terpenes do this with a higher yield than most molecules, but this is a really common process in the atmosphere. So its intensity and kinetics vary all over the place. Now, how many oxygen you add depends on how long this cycle goes. And the key point here, these are the termination reactions. These are hydroperoxides. This is the dimer at C20. Most importantly, in the real atmosphere, everything depends on NO, nitrogen oxide. Nitrogen oxide terminates, NO reacts with that peroxy radical, can react with it to form an organonitrate. And so, and now, flash forward a couple of years, Charian, who was one of my PhD students at Helsinki, who now is the professor. In fact, he has just been promoted to associate professor just now at Nanjing University in Suzhou in China. But this is my favorite figure from his thesis. Okay, this is now the nitrate films, not the epitaph. We're looking at the neutrals for a month in Utah in the springtime, and we saw, as we were saying, a bunch of homes. But now he did TMF on this, and these are the factors he found. This blue factor is the nighttime ozone plus alpha-pinene factor, or Pyle-Enz factor that happens at night. But during the day, we see a bunch of other stuff. And what's interesting here, this is the sunlight. This is the, this is interesting. This is the sunlight. This is NO. This is sulfuric acid. And if you look carefully here, I've got one factor that tracks the NO almost exactly. And another factor that more or less tracks the sulfuric acid. And now that I look at this, I never noticed it until now, we got another factor that more or less tracks the temperature. Now, the key here is that these are the mass spectra for those 7 factors. And the key here is the one at the top is the nighttime ozone plus alpha-pinene factor, and all these other ones are all dominated by organonitrates. Now, there's one thing to note. These are the mass spectra we get from ozone and OH. There's actually a little bit of nitrate particle in there, plus alpha-pinene, and from NO. I believe Hutala is the simplest photochemistry almost on the planet, because it's really only one VOC and the normal oxygen. And that's why we could figure all this out so easily. Everywhere else, these spectra are just really complicated because there are many molecules. But if I go back to, this is really slow. What's important here, the NO is an 80 ppt in Hutala. If you notice, the ozone is almost constant. This is considered very low NO. And that NO is enough to change the whole chemistry of these compounds. And if you're a nucleation person, a new particle formation person, these organonitrates don't play, are not nearly as effective in new particle formation as these non-nitrate homes. And the point is that this NO, I don't know about the ozone, and even this sulfuric acid were much lower 250 years ago. Utah is not pristine or remote at all. It's rural. It's not highly polluted, but it's totally influenced by Central Europe, Northern Europe. It is in no way representative of unpolluted air, okay? And the point is, this chemistry completely changed. What?
One question, why is that ozone does not have a very
Because there's much, why don't? Because the NO is so low. The ozone is 35 ppb, and it's only 80. You see, this is the NO titrating the ozone. That's the definition of low NO. Low NO is when ozone has a really weak diurnal cycle. If you're near a city or human activity, you'll never see this. It's a really important point, and that's true in most of the world. Okay, away from pollution. This is why I apologize. This is why I emphasize that I spent the last 20 years of my life, my career, studying clean air and polluted air. And now we figured out that clean air really is not that clean. So now the clean air I'm studying is in the Arctic or the Antarctic. And now we're starting to study in Southern Africa, in the bush, where there aren't very many people. And we're getting low. I mean, that's how you have to do to find really clean air. Okay? So I have this. So this is the schematic that we put at the end of the Julish paper. The idea here, this is schematic, we're going from nano CTN, 1 nanometer particles, to 100 nanometer particles. And the idea here is that in the current atmosphere, especially in the northern hemisphere, nucleation depends on sulfuric acid in the base, but then all the growth of the particle is organic. And my main contribution to this figure when we published it was to make this legible, okay? It really looks more like this. There is some extreme low volatility organic that actually is critical for the nanoparticle growth. There's a lot of low volatility organic that irreversibly condenses on ultra fine particles. NOx is really important. If you go to China, or I guess come here, there's a lot of this that grows the particles to make haze. And also here, but in other places. And this is all done. The point here is the growth of CCN on the current planet, when we reduce at least after we reduce SO2, we don't have huge SO2, I mean, we don't have huge SO2 polluting power plants, which all went away by 2000 in the United States. Organic are the main constituent, my main growth of CPN, and I think the majority constituent worldwide. So it varies, but all depends. And then, of course, in a place like India and other places, biomass burning has a big impact since it injects particles in these biomass to make this much more complicated. So, if I go back to this slide, this is what the AMF saw. This is what we learned from the epitoph and other experiments. And this is home to this, but most of this stuff actually condenses on here. And that's one of the key reasons, especially away from a highly polluted city, the O2C ratio is so high. Now, the final point is the concentration. Now, a key number to remember is if you have a ppt of condensable vapor in the air, and it condenses for 24 hours, that makes about 1 microgram per cubic meter of aerosol. That means that in clean region, all these molecules are in the ppt range. And if you're worried about the details of the nucleation process, it's the sub-ppt range. But this is why aerosols are so hard. Because, I mean, again, obviously, if you want 100 ppb in a day, you need 100 ppt to condensable material, but that's still sub-ppb. One of the reasons the aerosols are so hard is the concentrations are really low. And there are no shortcuts. And the final point is if you want to understand this, you need to get an AMS and you need to get a top SIMS. That's my one time when I'm a pure Aerodyne person, okay? Now, let's go back to the big picture. This is the cover of Science magazine in 2008, 2 weeks before the Beijing Summer Olympics. And the essence of the article about this is Beijing's air gonna look like this during the Olympics. Okay? And I mean, this is what the title means. It's a marathon. You're gonna run a marathon in that air, okay? And the fact is, it didn't look like this at all. It was pretty clean. And the next slide, which is the first AMS study in China, in Beijing. It was actually, this measurement was actually in 2006. And we published it in 2009 after the Olympics. But it explains why the Olympics, the Beijing during the Olympics was relatively clean. What's going on here, these are 3-day, 72-hour back trajectories. If you look at this, if the air comes from the north, the aerosol is relatively clean, okay? But if the air comes from the south, and these are short back trajectories, which means the air is pretty stagnant. That's when it gets dirty. And here, this is Hebei province. This is where all the industry is. This is the most industrialized province in China. So it's really clear when you get stagnant air drifting from the south, that's when Beijing has the worst haze. And I can tell you it does. I've been there during haze events almost as bad as the one in the picture. Now there are three reasons. Now the reason the Olympics were clean, relatively clean, there are 3 reasons. First, they got unseasonably more, half the air came from the north. Okay? It also rained a lot during those weeks. And then maybe most important is they shut down Beijing. This region was shut down for 4 to 6 weeks. Shut down means traffic was reduced, all construction was stopped, and they shut down much of the industry as possible. It's probably the only thing that was operating for power plants. And the air got cleaner. That was the first biggest real world air pollution experiment. And only the Chinese can do it. And the Chinese have done it multiple times since. Every time there's a major international event in China, the G20, I mean, anytime I used to be able to say, anytime the American president showed up, at a conference, or everybody showed up in China, they were shut down, like they had a World Expo. They shut down Shanghai for 2 weeks. They never did the experiment as well as this. They never shut down nearly as much as they did in Beijing. But at this point in time, the Chinese were fairly confident. They understood their air quality and they could deal with it. But the simple point is, shutting down Beijing is not a solution. Okay? They could do it once for 6 weeks, but. And what actually happened is the next 5 to 7 years, the air got much worse. They had many extreme haze, an extreme haze event in Beijing was 500 or 600 or even 800 microgram per cubic meter. And again, when the meteorology was like this, and out there in the winter, and on top of this, in the winter, the boundary layer gets really low and stable. That's when you get these ridiculous events. But starting in 2015, so what I just told you is the PM went like this between 2008, like this. It didn't go like, it went like this. I have the numbers here. Between 2015 and 2024, they reduced the aerosol by half or more than half. Most of it, but not all of it, was reducing SO2. Now, they really did it, and they think they have cleaned the air, though they know the air is not clean by international standards. They're beginning to lower. In fact, they are just right now in China. They are writing the next 5-year plan. The next 5-year plan is going to focus on ozone, reducing VOCs to try to reduce ozone, and they're proposing to lower their PM 2.5 annual standard to 25 it's at 40 right now, to lower it to 25 microgram per cubic meter. I don't know what's going to happen. But, and what's key here is this took 10 years. 10 years they cut PM 2.5 by more than half. And a problem is that ozone is going up. It's not going up quite as much as this slide says, but ozone's gone up by 10 or 20% in the same time period. And that's a classic air pollution problem that now they have to deal with. But that brings me to Pune, to India. Okay? I showed you a headline from 2008. Okay, now I'm getting ahead of myself. So, the Clean Air Act is the most successful legislation in the history of the United States. I mean, this was written by an environmentalist. I don't know. And in fact, it was really successful. Things like this don't happen in the United States at all anymore. Even LA is a lot cleaner, but LA has terrible meteorology and it's surrounded by mountains. And when the air comes up, they have a weak air breeze from the Pacific. The air can stagnate for 2 or 3 a week. It still can get dirty. But it took us about 40 years. In 1970 is the Clean Air Act, and I'd say this was true around 2010. Okay? Now, Googling this took all of 23 seconds. Okay? This was a headline in the New York Times from November 30th this year. This is perfect. India is a rising power, but breathing in air is hazardous. Okay? My simple statement is that in Mumbai last week, it was pretty hazy. And people told me, or said, was the worst air they'd ever seen in Mumbai. And obviously, the air in Delhi is often pretty bad. What I'm going to say to all of you is the pollution is only going to get worse. It's just people times GDP. Until your government, your society, all of you decide you have to do something, it just didn't work. That's exactly what happened in China. In 2008, they thought they understood it, but the emissions, everything just got worse in the next 5 years. So, this is 2025. And my question to you is, how long is it gonna take? Okay? This is up to you. And my final statement to all of you is whether it's air pollution or climate change, I believe we need people, I mean, attractive scientists, but we need people in every single country who understand what's going on. I mean, I think the bigger problem is climate change. But the immediate problem that nobody, that people don't, I mean, people do understand. And my simplistic way of looking at the world, if your government doesn't like headlines like that, okay? So that I didn't look because I know that Mumbai made the headlines too. Maybe not the front page recently, okay? So, and the most important thing, we now compare, let alone compare to 1970 in the US or 2000 in the US or 2015 in China. And we know a lot more. You don't have to rediscover everything we learned or the Chinese learned, we, the Europeans or the Chinese. You already have the fancy toys. Use them. Use them for India. I really mean this. And I am this crazy mass spectrometry guy. I believe measuring all those molecules helps you really understand what's going on. And I am so serious about that. But it's work. The toys don't give the answer. They give these really complicated spectra. The answer is analyzing it. I mean, and it's not easy, okay? The total pain sometimes. But the physicochemical information is there. And I didn't say much, I said just a tiny bit about cloud, but obviously all of this complex chemistry in submicron aerosol affects clouds too. And I'll be quiet now.
Can I have some questions now?
Excuse me, yeah, it's a very good talk. So you have covered most of the primary aerosol standards to the secondary aerosol standards. So it's very interesting to see that. And also very interesting pictures you have shown, the Beijing studies and other stuff. It's very, really interesting. So are you thinking that now India has the primary aerosol standards were very clearly defined. So do we need to put secondary aerosol standards very strong or something like that to reduce the pollution, like what you have suggested from the Beijing study? So they have been secondary aerosols has been need to be reduced unless you don't get this clear signal. So
No, what I'm saying, to answer your question.
Yeah.
And go back to this. What I'm saying is you need to do this study for every city, every region. And the point is, the primary is just this gray, okay?
Right.
And if you notice, when it's really clean, the gray can be relatively large, but it's still not dominating. Okay?
Right.
But my point is, every city, you make a map like this. And it depends on where the sources are. It depends critically on the meteorology. It's just that simple, but you have to do this. I believe this is the prototype of what you do. And obviously you put on here whatever you think is important. the total aerosol loading, ozone, CCN, but this is atmospheric chemistry. I mean, the more general thing to say, for example, is the solution to pollution is dilution. Whenever the dilution turns off, the air stagnates, that's when you have a problem. And you just have to understand it. I mean, which is more important, the dilution, how much, I mean, most of this stuff, if you're in Beijing, especially now, Beijing is now the cleanest city in China in terms of local emissions. Emissions are controlled in Beijing better than anywhere else in China, for sure. But they still get really hazy days because even though they have cleaned this region up a little bit, somewhat. I mean, when the air comes from Hebei province, you have a hazy day in China, in Beijing. And this is true everywhere. And it depends. The classic example in India, as I understand it, I'm not really the expert yet, is the crop burning and the IGP in the winter is trapped by the Himalayas and it moves south. Or it just stays there. And you have to figure out city by city, factory by factory, cropland by cropland, what's most important? And I am arguing really strongly, the more chemistry you do, I'm a chemist, I believe in my mass spectrometers, but the more chemistry you measure and you couple all this meteorology and you couple it to everything else you can find. I mean, if you have metal concentrations, NOx, NOx is really important, and ozone, it's all coupled together. And the more you study this or understand it, the more you can advise your government what's the most effective thing to do. And we understand it really well. You just have to adapt it. Okay, I can make another statement. The first ACSM in India, which came, I believe, in 2018, discovered in Delhi, there's more chlorine, sometimes more ammonium chloride in the aerosol, up to 100 or 200 micrograms per cubic meter, than anybody's ever seen in the world. And the ACSM said that immediately. And I'm not an expert, on where that's coming from.
In Delhi?
I thought it was in Delhi. Am I wrong?
Maybe it was in Kanpur.
Nature geoscience program. Nature geoscience program.
What do you mean? I just started to know. You have to know India better. I just know an ACF, and I wasn't part, the reason I don't know, my name isn't on that paper. I wasn't part of the study at all. I just heard it talked about. But my point is that was important. And the O2C ratio and all this stuff, it matters, okay?
Actually, in Delhi, it is not just one small city problem. Actually, it's a region-wide. So probably multiple needed.
You're exactly right. I know that. But Delhi is still easy for me. Okay, the New York Times. Oh yeah, they didn't say Delhi, they said your capital. When Americans whomever think of India, they think, especially now, they think of New Delhi, okay? And I'm still an American, okay? I still don't know India that well, okay? But
what I mean is that even there are some other parts also, it is even more polluted.
yeah,
Because it is a much more regional problem.
Kolkata is more polluted than Delhi actually.
But perfect segue. Okay, I will. This is.
But we have to learn from examples.
But look, now look, this is where the action is. Okay. More people live inside this circle
Yes.
than outside of it. Okay. And this is, I think this is called Asia. Okay. Now, in China, This is a triangle between Beijing, Shanghai, Xi'an, and Beijing. 10% of the population, world population lived there as of 10 years ago. I mean, the population of this region doubled or tripled since 2000 or whenever, okay? Because everybody moves from the countryside. It's also 10% of the world's GDP. You take 10% of the population times 10% of the GDP. This is the ultimate regional haven. It at its worst. It didn't look quite like that picture, but it was 100 or 200 micrograms per cubic meter or more for this whole region. Okay, that's when they had a problem. And that's no different, but now we're talking about the IGP, okay? They have cleaned this up by half or more, but now I'm gonna fast forward. This is now a pick plot of the world's megacities. Now in 2025, where China is the hotspot, so with India. But this is what it's gonna look like in 2100. Projected to look like. China's gonna go down. India's gonna grow some more. But all the biggest new megacities are gonna be in Africa.
Actually, by 2030, Delhi will be the highest populated city.
Okay. I mean, that's why I'm here. That's why you have an air pollution problem. That's what I'm trying to tell you. 30 million people don't come for free. If you want them to have cars and motorcycles and everything else, okay? But for example, I think the biggest challenge in the next 50 years is, can Africa do it even better than India or China? Can they not build hundreds of thousands of coal power plants, just skip millions, hundreds of millions of internal combustion engines and go straight to electric and solar and fusion or whatever? But that's the challenge for a planet. Okay?
But then you have the most sources of oil, reserve of oil in USA or Canada. We are underestimating in this.
Yes, I know.
Do you think it is biased? Towards-
Not only by it. I mean, look, I don't understand what you just said. I mean, if my country does not want, if my country just wants to drill more oil and sell more oil to 2100, then we have a problem. Okay? And okay. I have not changed my thinking about this slide since a year ago, okay? A year ago, I still believed in my country. Okay?
Maybe space exploration will, many people will find.
Anyway, I'm not gonna live long enough. Okay, you can do whatever you want. Anyway,
Yeah.
it's your turn. And
Let us can take more questions.
well, thank you.
Thank you very much. And maybe
I
there
think there's one more question.
Yes,
What is the mass to charge ratio? Mass to charge ratio shift in the AMS measurement, aerosol mass spectrometer.
what do you mean shift?
Mass
What
to
do you mean by shift?
one MBZ to and different.
I mean, the chemistry.
MBZ 60 is converted to MBZ 70. So during the high PM 2.5 loading,
Yeah.
how to resolve it immediately?
Well, the long answer is you just study it. I mean, I don't quite understand your question. The mass spectrum varies a lot because the chemistry changes and it's just buried in the detail. I mean, if the chemistry and the particles change, the mass spectrum changes. Those mass spectral changes, evolution are complicated. But, I mean, for example, to give a simple example, 60 and 73. MORZ 60 and 73 are the marker for fresh biomass burning.
Leo
Those markers disappear in 2 or 3 days if those aerosols are exposed to sunlight, because the levoglucosan reacts away. I don't know if that's answering your question.
That time, imagine that 60, that is leoglucosan. So those time, the peak intensive biomass burning is occur. So that time peak, we are not appearing.
Yeah, but it also depends on what type of biomass burning is. You don't see 60 and 73 if you have an efficient flaming fire. 60 and 73 mostly come from smoldering. So my point is the detailed mass spectra and the variation depend on the conditions. I mean, 60 and 73 are the marker of a fresh biomass burning that have smoldering. Okay? If you have a huge forest fire with the flames going up 100 meters, 60 and 73 are low. But on the other hand, if those two, there's an edge of the fire where there's smoldering. I mean, my comment is the variation, the huge variability in the mass spectrum, because there's huge variability in the aerosol chemistry. I mean, the other way to say it is when the sun comes on and makes OH radical, that's called low temperature combustion. The atmosphere is a low temperature combustor. So everything is changing. I hope that answers your question. Thank you.
If time permits, I have
Yeah.
one more question. So you mostly talked about the aerosol chemistry.
Yeah.
You also work on aerosol meteorology. Meteorology that is
Sorry, aerosol.
meteorology, the meteorology that is conducive for formation of aerosol and air pollution.
I'm sorry, I didn't understand. Aerosol
Meteorology.
meteorology?
Yes.
There is no such thing as aerosol meteorology.
Yes. So
Meteorology transports I mean, aerosols don't do the meteorology. The meteorology transports the aerosol. So that's what I was trying to say before. Every atmospheric measurement, you have to understand the meteorology, where the air came from.
no, so what I'm asking, have you, I mean, do you work on the stagnation events, air stagnation events? That
We're
is
doing
conducive
them.
for more.
I mean, that's just the weather. The stagnation has nothing to do with the aerosols. Except that it's not true. An extreme haze event can stabilize the stagnation and make it worse. But I don't work on that. I mean, that's a meteorologist. I mean, it's true. When it gets that hazy and no sun is getting to the surface, then that stabilizes the modulator and that can make everything worse. But I mean, it took me a long time. I mean, I was not trained as an atmospheric scientist. I've never taken a meteorology course in my life. It took me 25 or 30 years of studying atmospheric science for me to understand I gotta pay attention to the meteorology. Okay? And now I wish I knew more meteorology. Because it's all coupled. Okay, now, go ahead.
I had seen many pie charts for different countries where you see that organics is very high
Yeah.
compared to inorganics. So what is your opinion whether organics is harmful or inorganics?
I mean, that's a really simple one. Or the inorganics are not harmful. I mean, when you do health effect studies on ammonium nitrate and ammonium sulfate, they have no health effects. It's not really that simple. So that the bottom line is the organics, most of the toxicity is due to organics. But that doesn't mean the sulfate and the nitrate are, what do you call it? Safe. Because the sulfate and the nitrate provide the seeds to grow the organics. And the real purpose the most important thing is that the aerosol particles, the 102 100 to 500 nanometer, 0.1, 0.5 micron particles are the most stable. They stay suspended in the air. The only removal process, or the main removal process for submicron particles is rain. If it doesn't rain, they just last. They can last a month. And particles in that size range are the ones that get deepest into your lungs. So even if the particle is 60% nitrate and sulfate, if the sulfate and nitrate got it in the right size range and then it was covered in organic, it's still toxic. But I don't know if you want me to keep talking. PM 2.5 is a ridiculous number for health effect, but it's the only one we have. Everybody thinks it's not the total PM 2.5, as you indicated, it's specific molecules. But the size range is the most important because it gets into your lungs. And PM 2.5 is relatively easy to measure, and mortality is relatively easy to measure. And the correlation with excess mortality and high PM 2.5 is the best epidemiological environmental correlation there is. It's not because it's really the best one, it's just the data is the best. Mortality everywhere is more or less easy to tabulate, and PM 2.5 is also measured. But as you indicated, the details of what's really going on in the particle are a lot more complicated. So that the short answer, I gave you a really long answer. It's the organics, okay? But not everybody completely agrees with that. But that's what I believe. In fact, it's those peroxy radicals and those hydroperoxides. That's another point. Those HOMs are likely the most dangerous ones. Because those are the ones that when they get into your lungs, they start falling apart. And they're highly oxidized. They can make peroxy radicals, whatever. And I just told you everything I know. I really don't know that. But that's the point. And again, I think we didn't understand that in 2000 at all. Okay, that's 25 years of research. And of course, we still don't understand enough. But you get to take advantage of it and start from now, not 20 years ago.
So I think we can wind up the session now.